We're going to do a one-sided limit test for this sum, 1 over n cubed plus n plus 9. And it's important to note that we could have done a regular limit test if we chose the bn to be 1 over n cubed for this particular example. So when we're doing these limit tests, we need to have a sense of whether these converge or diverge. And this is likely going to converge because of that cube in the denominator. So that's one thing. We need to have a sense of convergence, divergence. The other thing is we have to have something to compare it to. So if we think it converges, we want to try to compare it to something that's also converging. So in this case, we're going to try the basal series, which is 1 over n cubed. 1 over n squared. So we're going to set up the limit. So the limit as n approaches infinity, and we're going to put the expression in the numerator. So 1 over n cubed plus n plus 9. And we're going to compare that to the basal series, which is a converging series, 1 over n squared. Okay, we're going to do this limit to infinity. We'll rearrange this first before we apply the limit. So in the numerator, we end up with n squared. In the denominator, we end up with n cubed plus n plus 9. Okay, so we can see that the power in the numerator is less than the power in the denominator. So we know that this limit is going to go to 0 as n goes to infinity. If it's equal to 0, we know that this does not pass our limit test, but we could maybe look at it from our one-sided limit test. So because it's going to 0, we can say that the bn in the denominator is more powerful than the an in the numerator, so that 1 over n cubed plus n plus 9 must converge faster to 0. Otherwise, this limit would not go to 0. So that red term in the numerator must converge faster. Therefore, we can make this conclusion. Okay, so the conclusion is going to look like this. We know that R, the basal series, we know this is convergent. Okay, we also know that the other series is more convergent. So we know that it is smaller. So we know that this 1 over n cubed plus n plus 9 is smaller. So we can conclude that this is also convergent. Okay? So then what we've seen then is that we've actually used this one here. We have Bn being convergent and An is less than Bn, therefore they both converge because we ended up with this limit of 0. On our chart here, we tested this side, the left side here. We had a converging series or sequence in the denominator. Our limit was 0, so that means that the an was smaller, so it must also be converging. We can show an inconclusive test for this one as well. So in this case here, we had a sense this was converging, and we chose a converging series to compare it to. So let's say that we chose a diverging series to compare it to. So we're going to set up this limit. So we're going to use the diverging series 1 over n. So we know that this is diverging this time. So we're going to set up our limit test. So we're going to set up the limit as n approaches infinity. And we're going to set this up as our 1 over n cubed plus n plus 9 over 1 over n. And this is going to be an inconclusive result. So this is an example of an inconclusive. Okay, so I'm going to again rearrange this. So the limit as n approaches infinity, we end up with n over n cubed plus n plus 9. We apply the limit. We have weak over strong, so this is going to be equal to 0. So notice that it's the exact same result as we got before. However, the problem is that we can say that this is a diverging series. This is diverging. And we know that the series that we tested is smaller than a diverging series. Well, smaller than infinity can still be infinity. So we end up with this. So we have a question mark here. This is inconclusive. We don't know, although we know it's smaller than diverging, we don't know if it's in fact converging. On our chart, what this is then is we're testing where B is diverging. So we have this diverging series that we're testing in the denominator, and we have that AN is smaller than BN, so that is inconclusive. So although we know that BN is AN is smaller, we're just saying that AN is smaller than infinity, which can still be infinity. So it's inconclusive. On our chart here, what we're doing is we're testing this part here. We had the diverging in the denominator, and we had this limit equaling 0. So it's going to this side, this left side of our one-sided test. But the problem is this is inconclusive. So we can say that the denominator is large and diverging, AN is smaller, but we still don't know that it is going to be small enough to converge.